Okay, so let us look at a little, Stats 101 example of statistical learning at work. And this is, what most statisticians actually do for a living, which is regression. Right? And in particular, let's look at linear regression because it's the simplest case. Okay? So what is the statistical learning view of this? Right? You may remember that you learned something like the following. Well, you learned the line, the line that you want is the line of least squares, which is the one that minimizes the sum of the squared errors, right? So let's first of all remind ourselves of what that is, or see it for the first time if you didn't take a stats course. And then let's see how we can arrive at this using our, notions of statistical learning. So here's the setting, right? Let's just say I have one input variable, x, one cause, let's say, and one output variable, y. And my model of what's going to happen is going to be the following. I have a true line f, right? So the solid line here, f, is the true function, right? Y is this function of x. But the data points that I get are corrupted by noise. So to the true function, I added some error e. So I get this point over here, right? Because there's measurement error, or there's whatever, there's sources of error. So even though the point should have been there, I really saw it here. Which means that the points that I get in my data set, they do not form a straight line. Okay? But what I really want to do is I want to recover that straight line from all those noisy data points. So what should I do? Right? And the traditional recipe is find the line that mix, here's my, the dashed line is my hypothesis, and the recipe is return the line that minimizes the sum of the squares of the errors between the points and the line. Right? Which means it's trying to be as close as possible to all the points, and whether they're above or below doesn't matter, right? Because the square is symmetric. Okay? Everybody with me so far? Okay, very good. So here's what I just said in a little bit more detail. My examples are pairs xi di, where di is the noisy training value. This is the data value. And what is di? Di is the true function f of xi, which in this case is a straight line, but it could be anything, plus a noise term ei. Okay? And let us assume, as people usually do when dealing with continuous variables, that the noise is just Gaussian, right? And there are many good reasons to assume that noise is Gaussian, including the central limit theorem that says just about everything becomes Gaussian if you have enough of them and they're independent. Okay? So E is a normal distribution. Okay? Okay, so now let's put our statistical, hat on. What do we want to do here, right? Well, let's make things very simple and again assume a uniform prior, right? So I just want to find the maximum likelihood hypothesis, right? So at this point I actually have everything I need to answer this question, right? I know that my noise is Gaussian. I know my data points. I know that my f is something of the form ax plus b, right? And what I want to do is I want to find the maximum likelihood a and b, right? The maximum likelihood A and B are the A and B that make the data as likely as possible. Right? The maximum likelihood notion is that your hypothesis is likely if it makes what you see likely. If you have a hypothesis that says that what you're observing is unlikely, that hypothesis is not very credible. Okay? So this is the task before us. So how do we do this? Well, as I said, we're going to wind up with this answer. My maximum likelihood hypothesis is the one that minimizes the sum over all the examples, I equals 1 to m, we're assuming there are m examples, of the square of the difference between the data value and the value according to the hypothesis. Okay? So I want my line to be close to all the data points as much as possible. Of course, you can't go through all of them because they don't fall into a line, so this is what I'm going to try to minimize. Okay? Everybody with me so far? Okay, so I just gave you sort of the punchline because you probably already knew the punchline, but the question is, how do we arrive at this, right? In Stats 101, people could just say, well, this is a good heuristic, right? Minimize the sum of squares. What we're going to see here is that this is actually the maximum likelihood hypothesis, right? And why is this the maximum likelihood hypothesis? Well, so let's apply our definition. The maximum likelihood hypothesis is the one that maximizes the probability of the data given the hypothesis, right? And now, remember, I have a bunch of data points, right? Each of these points is a data point, an x, y pair. And I'm going to assume that they're all independent, right? So once you've given me one data point, that doesn't tell me anything about what the next one is going to be like, right? They do not interact. which means that, and if they're independent, right, this means that the probability of all of them can be expressed as just the product of the probabilities of each one of them. This is a crucial thing that we do all the time in statistical learning. It's a simplification of the world, but it's one that makes things work. A lot of the time it's false, but we won't deal with that case here, right? I'm re-expressing my probability of my entire data set as just being the product of the probabilities of the individual data points. Okay? Everybody with me? Okay, and now I can just replace this by its expression according to the normal distribution, which is this slightly yellow looking thing. There's this normalization constant here. And then it's basically what? It's an exponential of a quadratic function of the difference between the data value and the hypothesis value. Okay? Divided by the square root of the standard deviation, which is the variance. Okay, so if the normal distribution is very wide, then things fall off slowly, right? You have something like this. If the variance is low, then the normal distribution is narrow, and the fall off is something like this. Okay? So this is what we want to do, right? We want to find the hypothesis, meaning the values of the slope and the intercept of that line that maximize this. Okay? All right, so how are we going to do that? Well, first of all, here's a very common trick that makes our life much easier, which is maximizing a product is a complicated thing. Right? So let's not do that. Let us take the log of it. Right? Why would we take the log of this thing here?
Becomes a sum.
Exactly. A log of a product is a sum. And a sum is much easier to deal with than a product, right? But now, am I screwing something up by putting in the log or no? I better not be screwing anything up, right? Because otherwise I can't do that, right? So why is it that taking the log here is okay? Remember, I'm just trying to find the hypothesis that maximizes this value, right? And remember, the log function is something that looks... Actually, let me put the axis here, right? The log function is something that looks like this, right? It has the very important property that it's a monad, so this is x, right? And this is log x, right? Log x is a monotonically increasing function of x, right? Meaning that when x goes up, the log also goes up, right? It never goes down, right? So how is that useful to us here?
Because that way the max will always be.
Yeah, if I find the max of the log, I've also found the max of x, right? Because they go up in lockstep, right? The log goes up less and less, but it can happen that x1 is greater than x2, but its log is smaller, right? So by taking the log, right? This is a very common trick, right? By taking the log, I have made my life easier. The values change, but the winner doesn't change, and that's all I care about. Okay. So I take the log, and so now what I have is a sum of logs, right? So we're at this line here now. Okay. Okay. So the first thing that happens is I can get rid of this part. Why is that? It's the same for all the hypotheses, right? This is just the normalizing constant that makes sure the Gaussian integrates to 1. It doesn't affect who the winner is, so that can go away, right? Okay, very good. So we're now at this stage. The next thing that can go away is the variance. Why can that go away?
Assuming it's the same.
Because it's also the same for everybody. By hypothesis, right? I've hypothesized that the variance was the same everywhere. The technical term for this is homoscedastic. I'm sure you'll really remember this, long after you've left this classroom. In reality, things might be heteroscedastic, which means you can have different variances at different data points, but that's a more complicated case that we're going to ignore. So this guy's the same everywhere, so again, it's a constant, then we can ignore it, right? So now we're at this stage. And now I can replace the argmax of this by the argmin of this. Why is that?
Because you flip the sign.
Yeah, I flip the sign, right? So if I flip the sign, the maximum has now become the minimum, right? I have turned everything around. Okay? So the argmax of this negative thing is the argmin of this positive thing. Everybody agree? Okay, so here is our good old sum of squares. Right? I want the argmin of the sum of the square differences between the data values and the predicted values.
If you get more data, then the variance will change.
What, sorry?
If you get more data to work on?
Yeah, so if I get more there, then there'll just be more terms in the sum. Right? It'll be a harder problem and more computationally expensive, but hopefully I'll get a better, fit at the end of the day, or I will have a higher confidence in my result. Okay? So what have we learned here, right? What we've learned is that if your noise is Gaussian, right, then what you want to do is minimize the sum of squares. So instead of minimizing the sum of squares just being something that falls out of the air, it's actually a consequence of the noise being Gaussian. And it also tells you that, well, yes, if you believe the noise is Gaussian, then this is a good thing to do. If you don't believe the noise is Gaussian, then maybe minimizing the sum of squares is not the right thing to do, and now I can do something else. So this is a very nice small example of how this statistical analysis can, number one, help you understand better what you were doing all along, right? But also help you understand when to do something different, right? Now it's not just like, well, pick whatever you like. It's, well, what is your noise like? If it's Gaussian, then do this. If it's not Gaussian, then what you need is you need the expression for the distribution of that noise, and then you go through the same exercise with that expression. Okay? So this is a very general recipe that will apply across a very wide variety of circumstances. Okay? Questions?
Can we replace squares of differences by just looking at absolutes of difference and summing them up?
You sure can. So nice application of what we've been looking at, right? So what would that mean? Right, so squared errors means the distribution of the noise is Gaussian, right? If instead of squared errors you just use absolute values, which by the way could be an excellent idea, what does that mean about my noise?
Uniform?
No, not uniform. Remember, uniform is the probability is the same, and then you get a sudden cutoff, right? And that's what happens here is that, like, with absolute value, you have a constantly increasing penalty, right? As your data point and your prediction move away from each other, right? So Gaussian, remember, a Gaussian distribution is, let's suppose that the mean is 0, just to keep things simple, right? So here's my x, right? And that x. So this is what a Gaussian distribution looks like, right? If you use the sum of the absolute values of the differences, what you're actually assuming is what is called an exponential distribution, which is something that looks like this. Because remember, the log of this is a parabola, right? That's how we got the sum of squares. The log of this is just something like this. So this is a linear function exponentiated, and that's an exponential log. And and you can play. You can imagine putting in other things and seeing what the corresponding probabilistic models are.
Laplace.
Yes, this is also called the Laplace distribution. Yeah. More questions? Okay, so why don't let's see. Let's go for a little bit more. Yeah, let's cover a couple more things and then.